I'm Bhavidhir V. Bharadwaj. Welcome to episode 36 of Genesis of Tomorrow. The following is going to be a conversation about cryptophysics, quantum information, the matter of ethics, and much more with Dr. Artur Ekert, a cryptophysicist, the founding director of the Center for Quantum Technologies in Singapore, and a professor at Oxford University. Also, folks, if you're interested in such deep science and deep tech conversations, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. And we're rolling now.
Cool.
Okay, if you had to explain to a child what quantum mechanics is in regard to cryptophysics specifically, what would be your elevator pitch? I think it would lay a very fundamental basis for people who are not really coming from a thorough scientific background to just get an idea about what the domain of cryptophysics actually is.
Well, it's tough, of course. We are touching two different points here, quantum and crypto, right? So those are two different areas, and somehow they became connected because, well, to some extent because of my work, I guess, and some of my colleagues. So first of all, let's talk about crypto, right? Let's talk about security of information and so this is a topic that fascinated people for many years. As soon as we learn how to write, we wanted to protect our secrets. So that means we want to share them with selected people, and so one way of doing this is to modify the writing that only say you and I can understand what it means, but nobody else doesn't. So, in order to do that, usually we have to agree on something, right? So, for example, when I write to you, the two of us have to agree on something of the type. Oh, look, I'm going to do a substitution. For letter A, I will substitute letter Z. For letter B, I'll substitute letter T, and so on and so forth. So that's one way of doing this. And there are many other ways of doing this, but all of them um, imply that this way or another we have to agree on something, on a method, how we are going to communicate so that nobody else can listen to it or eavesdrop on us. And so the question, of course, people asked, is it possible to design a method that will be secure so that as long as we follow a protocol, then nobody can really break the cipher? And it turns out that sometimes our agreements are such that people can guess by looking at the messages that we exchange. People can simply guess what is written there. One way, for example, to understand this is when we do simple substitutions. So, for example, if I write emails or messages to you and I use English language, and I try to follow our agreement, which says, for example, that for letter A substitute B, for letter B substitute letter C, and so on. Then someone who looks at those messages, not knowing about our agreement, how we decided to do it, can look at the statistics of letters, for example. We know that in the English language, the most common letter is the letter E. So if you see a sign in our messages, which is the most frequent one, then you can assume it's the letter E. And if you see another one that is the second most frequent, you assume it's letter T, and so on and so forth. So every natural language has a way to um, has a natural frequency of different characters. So there are ways of breaking ciphers without knowing about this agreement. So that's the story of security, crypto communication. And then, if you ask a question, is it then possible to design a cipher where that we can prove that nobody can break it, right? So perfect cipher. And the answer is essentially yes, but those substitutions would have to be very special. So there is a cipher called one-time pad where we can really show that this cipher is unbreakable. But there is a problem there, and the problem is that our agreement, our the way we agree to implement this cipher involves you and me sharing a huge amount of random and secret data. So that means prior to our communication, the two of us distribute random numbers that we keep. Those random numbers are identical, so you have the same. You have a copy of the set of random number that I have. So they're perfectly correlated and only known to you and me. So they don't carry any information per se. So this set of numbers do not have any doesn't have any information, and whenever we need to communicate, we take this set of numbers. It's called cryptographic key, and then we simply use it to turn it into a meaningful message. And it's known that this kind of cipher cannot be broken. The problem is how to distribute this randomness, how you and I are going to end up with different set of random, well, the same set of randomly generated numbers that is provably secure, secret, only known to you and me. And that is known as a key distribution problem. And this key distribution problem has been something that people working on the crypto side, on the really wanted to understand, find a method of distributing keys. So that's the story of crypto part until now. Then there's a quantum part to this story. The quantum simply comes in to solve the key distribution problem. It just simply says that quantum mechanical phenomena, such as a quantum entanglement, for example, allows two random numbers, identical random numbers, appear in two different locations. And by looking at some statistics of, if we repeat this process many times and look at some statistics, we can actually prove that it's truly random and it's known only to you and me, and it's in this sense it's secure. So it's a long answer to your simple question, but it's probably the best I can give. I don't know whether a child will really understand it in all details, but someone who is not a specialist will at least have some kind of a glimpse of the idea.
One another thing that I think that you can maybe break down in a better way and explain to people is this particular matter of generating a random number. Like generally, when you're coding, like Python, right? In high school, they generally teach you Python, and there's this function randet function. You go and you generate random numbers. Generally people do not know that the difference between what they are actually generating through those Python functions, generating random numbers, they aren't truly random. And like what actually, how difficult it actually is to, as you said, actually be able to generate truly random numbers at both ends. Could you maybe shed some more light in a more simpler way for people to actually understand what actually goes into trying to generate truly random numbers, and why is it such a big problem?
Yes, so it is a big problem because first of all, before we even answer these questions, we have to maybe pause for a moment and ask ourselves, what is randomness, right? How do we define randomness in the first place? And there are various ways of doing this, but one way, for the purpose of say this conversation, would be okay. A random number, or is I'll say a random bit, for example, like say 0 or 1, is a one that cannot be predicted So in other words, for example, if you are tossing a coin, you toss a coin and it's going to be either heads or tails, you know that, but usually you cannot predict the outcome. You simply say, okay, if it is a symmetric coin, it's a fair coin, so the chances it's going to show heads or tails are the same. But then you may ask yourself, okay, is it truly unpredictable? If I had knowledge of everything, all the laws of physics, like the position of the coin at the very beginning, the position of my hand, the state of the atmosphere, the wind, and everything, then the classical equations of motion, that what physics, Newtonian physics, the classical physics tells you, would actually give you the prediction. It may involve lots of computation. It may not be possible for all practical purposes, but in principle, it is possible. So in this sense, someone with a huge computational power may not find this unpredictable. This will be predictable. So then the question is, how do we think about this unpredictability? Usually, there may be something that is unpredictable to you because you don't know what's going on, but may be perfectly predictable to me. So you may perceive certain things as random, and I don't perceive them as random because I see how things happen. I may have more knowledge about something. So the people debated in the history of understanding randomness. People debated whether randomness is a lack of knowledge. Is it due to the lack of knowledge? So therefore, we say we don't know what's going to happen because we don't have the full knowledge. We can only just say what are the chances of something happening, that it's more likely that this will happen than this will happen, for example. So that is a subjective perception of randomness. Randomness that is due to the lack of knowledge. But people also consider an absolute concept of randomness. It's a randomness due to the lack of anyone's knowledge, saying that there's no entity on the planet that can actually predict the outcome of a certain experiment. And that is true in quantum physics. So where quantum physics differs from classical physics, it differs in saying that there are phenomena in nature which are truly unpredictable, in a sense that it's not our lack of knowledge about the initial state, about something. It is that the nature itself works in a random way. The nature itself has built-in randomness. The nature itself doesn't know what's going to do, which is quite a strong and actually quite profound statement about the world and the worldview. And so when we discovered quantum physics, we learn how to use this notion of randomness, of unpredictability, and use it to generate randomness, meaning something that the outcomes that you cannot predict. It's like a toss coin, like tossing a coin, except that this time, absolutely sure that nobody, no matter how much computational power you have, you will not be able to make predictions better than with probability 50%.
What are the current end-to-end encryption methods actually mean? How secure they are? Because surely the need for all the work that has been going on around in the cryptography domain is certainly due to recognizing the current limitations and challenges that, or even the lack of security, true security that the current methods may provide or facilitate. But to understand for a normal person, how do the current end-to-end encryption technology works, because that's one that people maybe utilize on a daily basis through their WhatsApp messages or whatever chatting that they do on different apps. How exactly does that work, and what the Probably the second part is what is different in the quantum side of things. Like when you go to the quantum cryptography side of things, how is it more secure in comparison to the current methods?
Mm. Well, the current methods, there are many, there's not just one, but there are many mathematical techniques that allows us to play with information. Some of them are based on difficult mathematical problems. So it's a way of transforming data um, using certain mathematical functions, which are sometimes easy one way but difficult to reverse unless you have some extra information. So, so there's lots of beautiful mathematics behind the way the current encryption works, and the the problem with those methods is that they are not truly unbreakable. Um, if you really base your security of your data protection on a mathematical problem that may look difficult, sometimes it's the question is it difficult only just because at the moment we simply cannot find a good solution to a certain mathematical problem, or is it inherently difficult? And it's usually format and latter. So it's usually difficult because we cannot find a good solution to the problem, but we don't know whether the solution will eventually be found or not. So that's a big issue. The other thing is that the progress in technology, faster and faster computers, not only classical but also the projected future quantum computers, will be able to deal with many problems that are behind the data security today. To mention only the RSA system, which relies on the fact that it's very difficult to decompose certain numbers into prime factors, and some other things used for digital signatures, for example, based on say elliptic curves and other algorithms. So it's altogether there's just mathematics behind. So when you think classical cryptography, most of the time you think, oh, it's protected because there's certain mathematical problem behind it. Whereas the quantum is different. It's not because there is a certain mathematical problem behind it, but because there are certain laws of physics behind it. And the laws of physics have different status than mathematical problems. So the laws of physics cannot be broken. The mathematical problems can be if you find a new solution.
um Taking it maybe a little bit further, what about if I send you a message, right, we chatted, and I asked you something like, hello Dr. Eckert, I'm sharing the meeting link with you. That would be categorized as a classical information bit, right?
Yeah.
What would be the equivalent in terms of quantum information? Like, how would that same thing look in the quantum perspective?
Um, Well, the quantum is usually what happens when you don't look at something. So it's interesting, but um, at the level of preparation and the level of receiving information, it looks pretty much the same. But what happens in between is the most interesting part. So the way quantum theory is designed is, I'm at least one way to talk about quantum theory is that. It's you do preparations and then you do measurements and you observe certain correlations between preparations and measurements. It's a very instrumental approach. I don't necessarily advocate this approach, but um, if we take this one, so the preparation would just be preparing a certain device that would generate a bit, but it may be that in between during the transmission period, this quantum bit will be prepared by a device in some very peculiar state, so that when you measure this state, you'll just see 0 or 1. But if you do repeatedly this, you will see that the 0 and 1, even though the preparations were identical, 0 and 1 appears with the same probability. So what I'm saying is that the physicists found ways of convincing themselves and convincing everyone else that in between the encoding and decoding, in between preparations and measurements, there is a bit of a quantum magic, that things are happening there and you don't see them literally, because when you start seeing them you have to make a measurement on this, and when you make the measurement then the things will kind of become like classical bits. So it's a bit strange world, isn't it? So it's somehow um, the interfaces we have with the devices is just like a classical world. We do some preparations, we do some measurements, but in order to understand the correlations between the preparations and the measurements, in order to understand how the measurements react to certain preparations, we do have to um, find good explanation. And this explanation involves um, saying that, that those data in between are neither 0 nor 1, but somewhere in between. It's strange, I know. So it's difficult to give a very simple pictorial picture of this. We learn to accept this by equations when we learn quantum physics, and we can see that the mathematics is working. So physicists agree on mathematics of quantum theory, but when you start asking questions about how does it really look, how does it really feel, then it's difficult, because even the question how does it really look involves the notion of the measurement, that you actually go and observe something because you look at it. But to be able to explain this in detail is extremely difficult, if not impossible.
So, like,
Well, I mean, it's just possible, of course, but without equations, it's lots of you would
tedious.
have to use all kind of analogies, which are probably difficult to find.
So, as such, from the user's perspectives, things would seem classical more or less, but
Yeah.
over the intermediary processes, that is where it's sort of a black box where things are going and it's quantum in a quantum fashion, which we do not really realize what exactly is happening. Because, okay, I think to some degree, we shouldn't really be able to know what exactly is going on to make it truly random, right?
Well, true. So there are two parts of your question. The first one is yes, you're right. It is like imagine there's a black box and we probe it. We just we press the buttons on this box and we see the lights flashing. And so by probing and seeing how this box reacts to us, we try to find a good explanation of what's going inside the box. And this explanation simply cannot be based on classical probability theory. We just want to, we find that there are some strange phenomena going on, and that requires the development of a quantum way of calculating probabilities. The second part is you ask whether the notion of randomness actually implicitly implies that you cannot explain it, right? Yes, so that if it is unpredictable, truly for everyone, so that means it just happens out of the sudden, and therefore there's no causal relation. There's no like a sequence of events leading to this particular event. So therefore, you're right. So it cannot be explained. It just happens.
From your end as a scientist, I mean, the main problem with quantum information is that it's so very fragile, right? uh, why exactly is that? And then from your end, while you're working with it, what are the things that you are maybe doing or trying to do in order to maybe make it work?
Yeah, so the reason it's fragile, if we were to use this analogy that you propose of a black box, so that we try to we by probing that black box, preparing and measure by preparations and measurements, we find out what's going on. And we know that whenever we measure something, it becomes classical, right? So we were talking about this. So it's the reason the quantum phenomena are fragile. It's not. It's that because it's not only you, but maybe there are other entities that want to look at it. So the environment, the act of um, looking at something or measuring something doesn't have to involve a human being. It could be a measurement can be performed by a robot, by another system. Even a simple interaction is a form of measurement. So one way of thinking about the reason why the quantum phenomena are so fragile is that the environment is whatever is around this quantum system, this black box, is trying to look at it, is trying to measure it, and is measuring it via some interactions. And by performing those interactions, just the whole thing becomes classical. So we just see all those quantum phenomena disappearing at the very fast time scale if we don't protect them. So then that brings us to the second part of your question. So what do we do in order to keep this quantum phenomena going, right? Well, there are two ways of doing this. One is via better and better isolation. So you isolate your black box from the rest of the world so that the world cannot measure it. But then if you have more and more components in your box, then it's getting a bit tricky. So those components start interacting a bit with the environment and with each other as well. So the best way to do it is, as we believe now, is to do the quantum error correction. You try to hide the quantum phenomenon or the quantum entity in a much larger entity, so that if there is a measurement performed by the environment, this measurement may not affect all the components, but the measurement. So the situation is, instead of having one system that we say, okay, the measurement may measure this system with some probability, we now prepare, say, 42 different systems. And so we say, okay, now the environment may measure, but probably will not measure all of them, maybe just measure just some fraction of those 42 qubits. And if it is some fraction, then maybe we'll be able to reconstruct our state from the rest. So that's the idea, roughly, of the quantum error correction.
The motive with while working in the quantum cryptography end of things is to create a robust, unbreakable defense system, right? But on in the similar breath, there is also the challenge or the potential for it to actually result in better, more powerful quantum based attacks. How exactly do how exactly do you think that the current methodologies, which stand no chance against a quantum based cryptographic attack, how exactly do you start substituting them from quantum defenses? Because right now everything is classical, right? The entire internet traffic, it all works on RSA encryption. How exactly do you start to substitute something that is so permeated throughout at such a large scale?
Right. So indeed, so most of crypto systems that we use today, the the overwhelming fraction of those is a classical system. There are quantum channels. There is a quantum cryptography already working in some cases, but that's really not well. It's certainly it's a tiny fraction of all systems that are available to us today. Um, there are two ways again to resolve this problem that you're talking about at the moment. So let me try to rephrase the question. At the moment, we use classical crypto systems, and we know that those classical crypto systems are vulnerable to quantum attacks. So once we have quantum computers, that are capable of breaking RSA and other crypto systems, many of those things that we use today will not be secure anymore. Not all of them, but many of them. So then the question is it possible to design a mathematical problem or a classical crypto systems that will be immune to quantum attacks? So even if we have quantum computers, we can prove that this classical system will withstand quantum attacks. Now, we don't have at the moment a good candidate that where we can say we can prove, but we can have like with RSA, we couldn't prove that classical computers. There's no proof that classical computers cannot break RSA, or we cannot find a fast factoring algorithm. It's just simply that nobody managed to find such one. So similarly with this new mathematical problems that we may have, we may just assume that indeed it may be difficult even for quantum computers to solve those problems in an efficient way. And there are the so-called lattice-based problems that were proposed as a new generation of protection. So the thing is to protect. So essentially, we would like to protect classical crypto with some classical ciphers that we believe might be difficult even for quantum computers. That area is known as a post-quantum cryptography or quantum resilient cryptography, and it is a big business. Many government agencies and that are certainly interested in having good standards, and National Security Agency together with actually NIST in the US had open competition for such a system that lasted, and the different candidates for post quantum crypto were evaluated, and the there are winners and there are recommendations that how to use the so-called post-quantum crypto. Whether those things are really secure, difficult to say. It's too early to say whether lattice-based crypto will be secure or will withstand quantum attacks. It's not entirely clear. There were many embarrassing moments during this competition. Some of the proposed systems that looked pretty solid and percolated to the final stages were then broken in a rather spectacular way, not even using quantum computer on the classical computers. But it looks like a reasonable choice to have the lattice-based crypto. It's just difficult to say how long does it take, or whether it is possible to break them using quantum computers. I don't know, but I personally I don't feel that lattice-based crypto will last, will withstand, will defend itself against quantum attack. So one way to go is, of course, to design those systems that are strong enough that even if we have a quantum computer, those systems will be secure. The other way to go is to use quantum crypto. And I'm not saying this is exclusive. I think that post-quantum crypto and quantum crypto should coexist in some sort of a hybrid form. And they will probably to offer better security. So even today, I mean, you can use post-quantum, you can put an extra layer of security on classical ciphers, so protect them with bits of a post-quantum crypto.
What about artificial intelligence and things like parallel computing? Like, are we really thoroughly sure that technologies like these do not pose any significant threats to the current classical setup? And our current classical setups are capable enough to fend off the attacks that these technologies may pose.
Yeah, well, certainly AI makes a huge impact on cryptography, just especially when it comes to code breaking. you're also code making. So but what I'm saying is just in cryptanalysis, um, it has its place for breaking ciphers as a tool for breaking ciphers, and also in it's a good tool for designing good ciphers. It's actually a wonderful tool in many ways. Now the so it is certainly a new tool for cryptographers both ways. And that is also a good, interesting tool for quantum computers in two ways. One is we use classical AI to design better quantum error correcting code. So you use it as a tool to think about the quantum architecture. And in the future, it's speculated, even though it's terribly difficult. It's speculated how quantum AI may look like. So when you just want to run AI on a quantum computer, there are many practical issues there. There's one, how you're going to take the classical data and prepare them in a quantum form. So there is this kind of input output problem, so that the way you want to collect data and just channel them through the to the processor unit, quantum processor unit, that could be a difficult part. That could be actually where things can go wrong. So lots of technical challenges and technological challenges and fundamental challenges ahead, probably solvable. And it would be absolutely fantastic to speculate how a quantum AI may look in the future. But it's just, I think it's probably much more difficult than to implementing quantum AI as compared to, say, implementing a quantum quantum computation. So probably early stages of quantum computation will be about something different.
How much time do you think it would take to scale up a quantum secured network from the experimental lab stage to actually being implementable to the global infrastructure? Like, how do you see that timeline be?
Well, it's difficult to speculate, of course, because it's all driven by not only by progress in technology, but whether something is needed by use cases and so on and so forth. So at the moment, it's certainly possible to have a large scale quantum crypto network, either with the help of satellites. So you can have quantum, you can have satellites that distribute the keys, and that's one way to go. And that satellite would work with the terrestrial ground stations and a network of optical fibers. Another interesting way to go is to work on what is called optical quantum repeaters. Quantum repeater is something that can regenerate the quantum signal. It cannot amplify it because that doesn't work in quantum physics, but at least you can repeat the signal and propagate it for larger and larger distances. So that is still work in progress, but there are many ideas how to do it, and that shouldn't be a problem. The question is, at the moment, it's just interesting research, and quantum crypto is being noticed as an interesting alternative to the more vulnerable and existing classical methods. But it's still a niche thing, so it will take some time before we start using the quantum tools in sort of like a daily data protection.
Quantum repeaters, a notch up to them, I think, should be quantum teleportation of information, really.
Quantum teleportation is something that you don't need a quantum repeater for quantum teleportation. You can set it up in the lab. It's an interesting concept where you can which has been implemented, but only at the level of individual atoms or actually individual photons. So quantum teleportation of larger objects is still a science fiction dream, but it's something worth dreaming about, I guess.
But in terms of specifically, let's say, bit size information, if you are aiming to teleport them from a particular location to another, what are the temporal dynamics like in relation to time? What is going on around there?
Um, the okay, the two things that are happening in the process of teleportation. One is the measurement. The when you there are those measurements that involve entangled particles, and the nature of correlations between these two particles is revealed as soon as you perform the measurement. And here, the temporal dimension is not so important. It doesn't even matter who measures first. However, that said, um, there's another element in teleportation where the sender has to send information to the receiver how to reconstruct the quantum state. And that travels with not faster than light. So, in some sense, quantum teleportation can appear on a time scale that is needed to send information from one place to the other, which is essentially the on the time scale dictated by the speed of light.
One another aspect is that of ethics, fairness, and equity. Like with every single technology right now, AI being the most pertaining example of it, uh, in regard or in consideration to quantum cryptography, how do we make sure that we are maintaining a fair and equitable demographic in terms of its access, scalability, utility, and in general enforcement?
Well, gosh, it's difficult to answer this question because, of course, those technologies are developed only in certain countries in the world because they still not. They still require basic research. They still require lots of improvements, and they still require lots of investment and a certain know-how how to do it. So those technologies are eventually they will be available to any country, but I think and probably much cheaper. But right now, it's just just the quantum research is certainly focused in countries that can afford to develop quantum technologies, and there are many of them. And by no, just the social aspects of it or ethical, because there are many. I mean, like ethical, and we can ask about the use of this, right? You probably this what you have in mind, or you mean in mind access to quantum technologies? Well, access is probably will be dictated by how cheap eventually those technological solutions will be for countries to afford them. Which I think that there are many countries in the world where there are research labs that are capable of setting up simple quantum operations and quantum technologies.
What about the regulatory and regulation aspect of things? Like, how do you imagine the regulation or the regulatory bodies in relation to managing quantum secured information or the quantum systems networks?
Yeah, at the moment, at the technical level, the standards, international standards, are very important, of course, because you may have one device developed by people in India, another device developed by people in the United States, and even though the two of them may be based, both of them may be based on quantum technology, on similar methods, but without agreeing how to inter it's still maybe not possible for those two devices to talk to each other if they're based on a different standard. So the big thing is to agree on standards in quantum secure communication, for example, and that's going on. There are standard bodies that are looking into this. In terms of the legal framework and the legal requirement, that I don't think that is going on. I think that will probably just be under the purview of if it is a secure communication, there will be probably a legal umbrella related to secure communication, because the it will be probably the use cases, the end sort of application. Even though it's based on quantum, we are now looking at what does it do, right? And if it is to protect information, I think the same legal packet that is used to regulate how secret information is handled will be probably applicable to this case, except that the quantum will offer much more significant security.
What sort of stack of skills do you suggest people who are starting out in the domain to develop or work upon in the early days while they are getting into it?
Well, the quantum to be able to do quantum technology, you have to have at least basic knowledge of quantum physics, and then of course the on the experimental side, there are many different technologies that support quantum phenomena. Quantum is more like a a theme, the way how things happen. It's a way of how we calculate probabilities and chances that something happen. So underlying technologies, there could be many of them. You can build quantum devices based on with photons. You can build quantum devices made out of individual atoms that are interconnected in some way. You can use trap ions to generate quantum phenomena. So there are many possible ways of doing it. Um, and so, with what kind of technology one can develop really depends on what kind of specialists you have. You may have quantum opticians, and then they know how to do quantum with light. You may have people in atomic physics, and they would know how to do quantum with individual atoms. Those different technologies, some of them are cheaper, some of them are more expensive. Probably quantum optics is more is cheaper than many other. But so the set skills that you need to have is on the background general science. You need to know quantum physics. In terms of practical knowledge, you need to be able to uh, do a very simple experiments. You can be a quantum optician at the engineering level. You can be atomic physicist, but then there are certain generic experimental skills plus understanding how to set up quantum.
But there's also this other thing where this very plethora of things that you can choose from as to what you want to do, that leads to being the primary source of confusion that young people generally have as to, because when you're young, you generally want to stay relevant in the long term from a career security point of view. And as a researcher, how would you suggest them that they maybe tackle or approach this particular question that invariably may arise?
Well, it's very difficult to give a generic advice for people how to proceed with their interests and careers. One would say that the best is just to follow your interests, because um, whether it's quantum or something else, it's only when you are truly interested in something you'll be able to devote your time, your focus, and your energy into the set of problems that you have to solve. Um, Quantum is not different in terms of many other areas where I require problem solving, so general problem solving abilities, right? So we are talking about analytical thinking, rational thinking, dissecting problem into pieces. So one can say that there is a general set skill to help us to tackle with problems, and those some of those mathematical problems that people deal with quantum information science in data security are not easy. So, um, but but I think there's if there's only one advice one can give is just like follow your interest, follow your instinct, just and it may not always be most profitable path in your career, but at least it will be rewarding.
You worked years and years on end in this particular domain, right? How do you feel your temperament in your particular subject matter, but also the in general way in which you approach different problems or matters that has evolved?
Yeah, well, of course it has evolved. Like in science in general, right? Especially on the mathematical side. When you are young, you are much faster. Your abilities to calculate, to see mathematical structure are way better. I mean, they then I guess I was certainly much faster in in my algebra when I many years ago. But over time, you start compensating this with a little bit more experience and some insights that you didn't have. So there is a interesting trade-off. I wouldn't say that the older you get, less creative you are. In fact, but there is some kind of a change how you do science. Uh, then I think you become slightly more sophisticated. You can connect dots. You know more, so you can connect dots between different fields. You can probably visualize certain things better. You develop certain intuition for things. Quite often, you don't have to do those calculations because you can see this result, or you can see the some aspects of this result that otherwise would take hours and hours and hours of algebra. So the in the community, right, when we have both younger research and older, less experienced and more mature researchers, that's wonderful because you can, working as a team, you can just complement each other. Those much more experienced can offer some insights and certain intuition. Those less experienced can offer better, maybe mathematical skills. So that works pretty much. So I wouldn't worry too much. I would just say, just carry on and do what you like.
What was the and what even is the most intriguing aspect of your work for you?
For me, it's being a scientist has lots of privileges. I would say you feel privileged because you're part of international community that doesn't know the borders. The language doesn't matter. We usually communicate in English, but the language of science. I mean, the religion doesn't matter. The your political views do not matter that much because if a mathematical theorem is proved, it's proved, right? So it doesn't matter who proved it, and it just um, so the science doesn't know the borders, and that's a beautiful thing. So you meet people, you meet the most interesting people from all kind of places in the world, all kind of backgrounds, with wonderful stories to tell you that enrich your life. I don't think that there's such egalitarian community where people can really just across different ethnic groups, religious groups, you name it. We can be as different as you choose to be, um, but nonetheless, there's something that unites us very deeply, and this is actually this curiosity-driven scientific discovery, and I think that's wonderful. So that's I value a lot because I don't think I would, if I were to become, I say, investment banker, for example, I don't think I would have this ability to see and perceive the world as I do as a scientist. But then maybe, of course, we might be missing an interesting perspective that can be offered by people working in investment banking. I'm not saying this, but what I'm saying is that this perspective that science offers is absolutely fantastic. And the other thing is the thrill of discovery. Sometimes you have all kind of issues that you have to handle, all kind of daily problems, but somehow when you enter the world of equations, the world of formula or mathematical concepts, it's like a comfort zone. It's just maybe escape, but it is a sort of interesting comfort zone, which is great. And I personally would like to understand the nature of randomness better. Why is that so? That nature can generate things without any reason or cause for it. But is it true? Maybe it's not true. Maybe our worldview is just not yet good enough. Maybe there is something there that we don't understand. So there's a lot there to work on and to understand better.
I've come to sincerely believe that scientists and scientific endeavors in general are always way more capable of touching lives to the extent that they do. And what I mean by that is because a scientific piece of work is able to affect humanity at large across generations, regardless of whatever you contribute, how minuscule you think your contributions are. It invariably, inevitably is bound to impact the entirety of humanity across generations.
Yeah, absolutely. Yes.
And
Yes, I think.
I think the aspect of you wanting to understand randomness better, a speculative thought trail of sorts, I think I'm curious to ask you is the entire aspect of entropy and randomness has been persisting throughout the existence of not only our humankind but like the universe itself. We do not really know what instigated or caused the Big Bang. It happened. And so, from a general perspective point of view, that itself, the creation of everything that we know itself is random. How exactly do you, from your perspective, this randomness takes play or just happens in that humongous perspective or landscape?
Well, how random? Well, there is of course a question of meaning in the context of randomness. Like, what's the meaning of the universe? If there is a meaning to the universe, if it is random, what's the meaning to anything, to life? If it is random. I find it difficult to answer these questions because it's as a scientist, at least, at this point, we just venture into more philosophical aspects of science, or even theological, I would say. Um, I just would probably be reluctant to go there because but it is a very good question, and I don't know whether science will ever be able to answer this question.
There's this final question that I like to ask each and every guest that I have on the show, and it is, what exactly would be your word to humanity at large?
What exactly would
Would be your
I?
word, your message to humanity at large?
I think that I wish people were to entrust their actions to the power of reason. Uh, so I think so much is going on in the world, right? So and our actions are driven by all kind of things, and good reason and good explanations should make our decisions better and eventually um, make life and the world better, I guess. So I want to believe in the power of reason, and I would love people to believe in the power of reason, power of rational thinking. But that's not the message; it's just a wish, right? So it's yeah, that's it's or maybe I just wishful thinking, of course. But The message would be that the problems we are facing, and there are many problems humanity is facing, right? Big and small, from climate change to all kind of other issues. I think that the problems are usually solvable. And I'm trying to be optimistic here. I would say problems are solvable, but we have to entrust our reason and somehow follow the path of reason.
Dr. Artur Ekert, thank you so very much for being on the show and just spending all this time very graciously to break down all these different facets of your work that you have been doing. It was a delight talking to you.
Well, thank you for having me. I enjoyed our conversation very much. Thank you.
Thank you so much. Okay.